Hello, I'm Lily Long, and today we're going to revisit charge tapes in Physics 2, Lab 2, Lines of Charge. We'll be exploring the method of distributed charges by taking the electric charge of a charged object and evenly dividing this value by the number of small pieces decided upon, each known as dq. We can then use the point charge Coulomb's law to calculate the electric force based on the collective interactions of the distributed charges on objects like the tapes from Lab 1. For this lab, we were required to approximate our final charge for the line charges by how close we could get to our electric force magnitude to the gravitational force, as both are equal and opposite amounts that cancel out, and allow for tape B to levitate above tape A. The final approximate electric charge of the top tape was 3.0585 times 10 to the negative 8 newtons per coulomb, which is 1.92 times larger than our point charge electric charge, which was 1.59279 times 10 to the negative 8 newtons per coulomb. Lab 1 introduced us to the charge tape system, which calculates the excess charge on ordinary objects such as Scotch tape. We were able to measure the length of each tape and the distance between two charged pieces when the top tape's electric force cancels out with the gravitational force. With the help of Coulomb's law, which provides the electric force between two charged objects, we used their law that explains the cancellation of tape A's electric force on the tape B by gravity, and how similar charges, such as those of the two pieces of tapes, repel each other. This experiment informed us that either the tape's point charge is 1.59 times 10 to the negative 8 newtons per coulomb, and the ratio of electrons to atoms on the surface area of one side of a tape is 1 to 3.82 times 10 to the 6. Glow script was mainly used in this experiment, and three measurements we needed were the mass, which was 0.00019 kilograms, the distance between the tapes, which was 0.035 meters, and the charge, but this was altered later on. First, we established our electric field function, which calculates the electric field based on certain observation and source locations of objects. Then, with the use of a given line charge function, we can separate the pieces of tape and represent them as two lines of spheres, with each sphere, dq, having a q divided by n charge, with q being the total electric charge and n being the number of spheres in each line. For this experiment, 10 spheres were utilized, with the red top line of spheres representing tape B and the blue bottom line representing tape A. The electric field scale turned out to be 2 times 10 to the negative 6 for it to be appropriately visible. For the electric field, we iterated through each sphere in the top red line and implemented a green arrow starting at 0, 0, 0. To calculate the total electric field, we used the E-field function and accumulated the individual electric fields to get the sum. To calculate the total electric force at the top line charge, we multiplied the individual charge of each dq by the electric field at each dq and accumulated these terms as well. Green arrows were then created on the top line based on the scale used to make them appropriately visible and their own total value E at dq top. Finally, the net electric force arrow is created in white, pointing upwards because it's tape A onto tape B, as well as the gravitational force in yellow created by multiplying the mass of the point charge of the tape by the gravitational constant. Our aim was to have the electric force from the line charge method be as close to the gravitational force of tape B in order for both to cancel each other out. This magnitude was around 1.863 times 10 to the negative 3. For this experiment, we assumed the air resistance was negligible. We could represent the tapes as point charges with all the tapes charge concentrated at the center, and that each tape had the same amount of evenly distributed charge. Some things to consider are 1. The line charge and point charge methods required two different Q values, with the line charge method having a charge value of 3.0585 times 10 to the negative 8 newtons per coulomb, and the point charge method's charge being 1.59279 times 10 to the negative 8 newtons per coulomb. And 2, these estimates differ because the point charge is only one aspect or term of superposition, which is a method of calculating electric field throughout the sum of different electric fields of different point charges. When we used the line charge model, we were dealing with multiple point charges, where the electric charge of an object is distributed through all the created point charges, dq. The line charge is more likely to be closer to the real value because it can more accurately represent the area of an object as it represents broken up pieces of an object's total electric charge. This is similar to the Riemann sum integral concept, where the smaller the distances are, the more accurate the approximations are. Thank you for your time, and see you next lab.